All right, I'm starting to make silly mistakes here. So anyway, outside this parallel plate capacitor, the electric field is zero. All the electric field is contained inside here, okay? Because this negative charge attracts an electric field coming in, and it's getting it all right here. This one pushes the electric field out, all right? So the electric field outside of this thing is equal to zero, okay? All right, electric field lines provide a map of the electric in the space surrounding the charges. Okay, here's a positive charge. Now we could also, double them if we wanted to, because in other words, this one has this positive Q here, just looking at this representation, and if we're saying this is of proportional representation, this has a lot stronger electric field. So I would guess that Q is bigger because the electric field depends on Q, how much charge of that big Q charge you have there. And so that one's got more electric field. Notice negative field lines for negative charges come towards it. All right. Electric field lines begin on a positive charge and end on a negative charge. In other words, the electric field lines, they're kind of like eHarmony. This negative charge is looking for somebody and the positive charge is looking for somebody, and they hook up. All right. So you get a little bit of a bubble here at the end on these parallel plate capacitors, just a little bit. For our purpose, school book purposes, schoolhouse, charge outside the capacitor is zero. All right. This is what is known as a dipole. The number of lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. Okay. Amount of charge leaving is proportional. All right. Notice field lines cannot cross. There are three things wrong with part A. What are? Well, let's take a look. First of all, this is a 4, and the negative ones add up to -4. First of all, we've got field lines crossing here. Can't have that. Okay. So far, so good. It's pretty good in that this is going towards, and this is going towards. Three things wrong with part A. Okay. This one is absolutely correct. All right, and if 4 are going this way, then 2 should be going here, and 2 should be going here. So that's a total of 8. The proportionality is right. The proportionality is not right for this one. Well, this has a total of 8, and this has 1, 2, 3, 4, 5. Yeah, see, that's wrong. That 5 is wrong there, 4, 5. It should be in the same proportion. So at least these are in the same proportion, but they cross. So the proportion is wrong here. I don't know why they didn't say part A and B. Okay? All right. Electric field inside a conductor. This is what is known as shielding. The electric field inside a conductor under electrostatic conditions. This slide is a classic for those pesky conceptual questions that I ask, all right, on tests. Okay, so at equilibrium under electrostatic conditions, any excess charge resides on the surface of the conductor. So if I would able to inject a bunch of negative charge in here, they'd all come out just like on the John Travolta thing. They'd come and hang out on the outside. Okay. The electric field inside here is 0. Okay, because remember, the electric field on the inside there is 0. The conductor shields any charge within it from electric fields outside the conductor. So this is why black boxes on airplanes, things like that, are made out of metal and not rubber or wood or some other non-conducting thing, because the charges will the negative charges will attract any other electric field is going to hook up on the outside, and the inside electronics will remain solid. Okay. Okay, the electric field just outside is perpendicular to the surface. All right. Notice how the negative charges of the sphere have lined up on this side and the positive charges lined up on this side. Inside the cavity is 0. And I'm telling you right now, we're doing that all conceptually. The mathematics of that is a burger. So now, notice what happens. Here's shielding again. Electric field's inside a conductor. So let's go ahead and put a charge inside this conducting sphere. So what's going to happen? The negative charges are going to line up on this rim, leave it positively charged out here, and these positive charges are going to be proportional to this positive charge here. Okay? And I can figure out what outside of the surface, if I have a charge, I can figure out what, this is a sphere, I can figure out what, this is Gauss's law, so I'm going to stop here and we'll come back.